The mean value theorem, section 5.2. Moving through, we're application to derivatives. Different ways to use all those derivative techniques that we've learned in the last few chapters. So let's focus on a couple. Through this chapter, we're going to learn the mean value theorem, physical interpretation of it, increasing and decreasing functions, and any other consequences of this. The mean value theorem is an important theoretical tool to connect the average and instantaneous rates of change. So, let me look at the next one. If mean value theorem, this is the mean value theorem, if y is equal to f of x is continuous on every point on a closed interval AB. So let's talk about it. It's continuous. Oops. Get my pen out here. It's continuous as a point, closed interval AB, and differentiable at every point as of its interior. Notice it's not closed, it's interior points. Then there is at least one point C in AB such that f prime of C is equal to f of B over f of A minus B minus A. So there's at least one point. Could be more, but there's at least one point. So if this doesn't fail, something else is wrong. So let's say, for example, show that the function x squared satisfies the hypotheses of the mean value theorem in the interval 0, 2, and then find C. First of all, it said it has to be continuous. We know that x squared is continuous on the interval 0 to 2. And we know that x squared is differentiable on the whole interval from 0 to 2 open interval. So now if we went through and figured out a few values, so let's plug in, let's figure out what f of 0 is. F of 0 is 0, f of 2 is 4, and f prime of x is 2x. Now if we follow this formula, it says f prime of c, so that would be 2c is equal to f of b. B is going to be my second interval, f of 2, so it would be 4 minus f of a, which is 0, over b minus a, 2 minus 0. So what we have here is 2c is equal to 4 divided by 2 is 2, so c is equal to 1. So at 1, at the value of c equals 1, the derivative is equal to the average. And that's what this says. The instantaneous, this is what mean value means, and I'm not going to write this down, you might want to listen closely. The instantaneous change is equal to the average change. That's what the mean value theorem says. Instantaneous change is equal to the average change. So if I was looking at this graph, and it's going to be hard to see, I'm going to erase a little bit here. I'm just going to get rid of this here, out of here, delete, and I'll just erase this out of here too. So in other words, the average change is a straight line. Instantaneous range is that those two slopes are the same. This is what the mean value theorem means. Now some other things. Increasing functions and decreasing functions. Let f be a function defined on the interval I, and let x1 and x2 be any 2 points in that interval. If f is increasing on I, then for all the values x1 is less than x2, the y values have to be less. So therefore, as the x increases, y increases. That's an increasing function. Decreasing, as x is increasing, y is decreasing. And we're going to look at different ways to find this as we go through too. Correlate. If f is continuous on AB, closed, and differentiable on open interval AB, then the derivative is greater than 0 from each point on AB, and f increases on closed interval AB. Notice the increasing, decreasing. It increases closed interval. Means we have the brackets around our increasing and decreasing. If f is less than 0 on each point of AB, then f decreases on AB. So if the derivative is negative, it's decreasing. If the derivative is positive, it's increasing on that interval. So let's look at this. It says, where is the function increasing and where is it decreasing? So let's take the derivative of this. So we know that f prime of x is equal to 6x squared minus 12. So if we factor that out, we get x squared minus 2. And now what we're going to have here is we want to know when it's decreasing. If it's decreasing, that means it's the derivative has to be less than 0. So therefore, 6x squared minus 2 is less than 0. X squared minus 2 is less than 0. I want to divide by 6. X squared is less than the square root of 2. Oh, sorry. X is less than plus or minus the square root of 2. And that gets to be kind of tricky when we start doing these square roots. So I'm just going to plot these. So what I'm going to do is I'm going to put negative square root of 2 here. I'm going to put a positive square root of 2 here. Negative square root of 2 is 1.4, so negative 2. Let's plug in negative 2 here. 4 minus 2 is 2. It's positive out here. If I plug in 0, it's going to be negative in here. If I plug in 2, it's going to be positive out here. So where is it increasing? It is increasing, and I'm going to put it here. I'm going to extend this down here a little bit. This function is increasing from a negative infinity to a negative square root of 2. Now, infinity doesn't have one, but we're going to put a bracket around this. Union with bracket square root of 2 to infinity. It is decreasing from a negative square root of 2, and I keep forgetting my bracket, to the square root of 2. And I like to do it in the line method. I like doing that. We're going to do more of that next section too. I don't like doing all the rules and everything to figure out where it's decreasing, increasing. Do the line and plug it back into your derivative. Now corollary. If f prime of x is equal to 0, in other words, if my derivative equals 0 at each point on an interval, then there's a constant c for which that function is equal to c for all x in an interval. In other words, if the derivative equals 0, that means it's a constant function. Pretty much, if the derivative equals 0, it's a constant function. Let's go to the next one. Oops. Next one. If f prime of x equals g prime of x at each point on the interval I, then there's a constant c such that the f of x equals g of x plus c for all x in I. In other words, if the derivatives are equal, they are only going to differ by a constant. They're not going to differ by much more than that. Now, a function f of x is an antiderivative of a function f of x if the derivative of f prime of x equals f of x for all x in the domain of f. The process of finding an antiderivative is called antidifferentiation. Now, we're not going to do a lot about it. Really, the process of finding the antiderivative is integrals, but we're just going to look at some of the basic ones to find them. Notice how they wrote down the antiderivative is a capital F of x. That's how they write antiderivatives. So let's just do one example. Find the velocity and position functions of a free-falling body in the following set of conditions. The acceleration is 9.8 meters per second squared, and the body falls from rest. Okay, first of all, we know this. We know position, and the derivative of position is velocity, and derivative of velocity is acceleration. So if we go backwards, it goes that way. We know on this problem that the acceleration is 9.8. Now, from our previous rules, now we know that velocity acceleration at any time, I should put in there. Now, the velocity at any time is equal to 9.8 t plus c. Now, why did I get t, first of all? If I take the derivative of this, derivative of 9.8 t is 9.8. That's what I have to get to acceleration. So I just added a t. If I take a derivative of a constant, it's 0. I wouldn't have it. So if I took the derivative of velocity, I would get acceleration. Now we need to know what is c. The body falls from rest. That means my initial velocity is 0. So v of 0 is 0. So 0 is equal to 9.8 times 0 plus c. So c is equal to 0. So my velocity at t is 9.8 t. There's my velocity formula. Now we have to find the position formula. Now we're going to go back one more step. Now that's going to be a little harder one now. Oops, wrong way. Now position means we have to say what can have the derivative of this. So we're going to add 1 to the exponent and we're going to divide by that. So what we're going to do is we're going to get 4.9t squared, and we always add on a c. Now we can check it. Take the derivative. 2 times 4.9 is 9.8 t to the first because we subtract 1. Derivative of a constant is 0. So we would get that equation. But now we have to find it. And the position at time 0 is 0. So we're going to say 0 is equal to 4.9 t squared plus c. And the t is 0. So that ends up being 0 is equal to c. So my equation now is my position equation for this function is 4.9 t squared. Tougher problem, but we'll get through some more of those and ask some questions on those. That's it for this section.